Hello everyone, my name is Alejandra May and I'm a senior studying anthropology at Purdue. Every year, thousands of species go extinct around the world. Many scientists believe that this could be the onset of a sixth mass extinction. Although animals can rebound from such events through ecological processes, these can take between 5 and 10 million years. In light of the current situation, my objective is to understand the causes of past extinction events, specifically the extinction of mammoths and mastodons at the end of the Pleistocene in North America. In North America, mammoths and mastodons are the most well-studied extinct genus from the end of the Pleistocene. Over the last few decades, various hypotheses have emerged to explain their extinction, but three main hypotheses have risen to prominence: overkill, climate change, and a combination of both. For this project, my first task was to collect and compile the known sites in North America that contain proboscidean remains. After, I collected radiocarbon dates and latitude and longitudes for each site, which then served to complete a paleoenvironmental reconstruction. Lastly, I completed a principal components analysis and subsequent Bayesian regressions. Figure 1 shows a map of all the sites collected for this project. This data is what allowed us to complete a paleoenvironmental reconstruction of each site. A paleoenvironmental reconstruction allows us to study the variability in temperatures and precipitation at a certain place and time. The PCA demonstrates how each variable relates to each other and tells us if certain variables correlate. We began our analysis by using a PCA plot to graph PC1 against PC2. In this plot, the red dots represent mammoth sites and the black dots represent mastodon sites. We conducted a vector analysis to visualize the effect of the paleoclimatic variables and time on the PCA. A vector analysis shows the direction and magnitude of an effect. Our paleoclimatic variables included temperature and precipitation seasonality, mean annual temperature, and annual precipitation. Here, PC1 accounts for approximately 56% of the variation, while PC2 accounts for a further 25%. The blue vector shows the direction and magnitude of time, however, it was not used to construct the PCA model. Instead, it shows the relationship of time in the model. Now, by looking at PC1 on this graph, the values closer to 3 indicate a higher mean annual temperature and precipitation seasonality. But as we move towards -3, this indicates more annual precipitation and temperature seasonality. Since PC1 accounted for 56% of the variation, we used it as a proxy for environmental variability in the following Bayesian regression models. The first model examines the linear relationship between time and the environment. We determined that time has a significant effect on the environment. The plot shows this linear relationship. Note that time is reversed on the x-axis, meaning that as we move to the right on the x-axis, we move closer to the present. This model indicates that the environment is changing with time, and specifically that the composition of the proboscidean community is affected by this shift. The second model examines the interaction between time and species and its effects on PC1 as a proxy for the environment. We determined that there is a significant effect of the interaction between species and time on the environment. This plot may be slightly confusing as we had to flip time on the x-axis, so now the further to the right, the more one moves into the past. This plot suggests that mammoths in blue and mastodons in yellow occupied similar niche spaces at approximately 16,000 years before present. The niches they occupied became increasingly different as they moved through time. Here, the niche of the mammoths appears to shift drastically, while the mastodon niche space shifts very slightly and almost not at all. Closer to 16,000 before present, mammoths and mastodons occupied a niche space with higher temperature seasonality and annual precipitation, and lower mean annual temperature and precipitation seasonality. However, when the mammoth niche space begins to shift upwards, it moves into a space with higher mean annual temperature and precipitation seasonality. Therefore, the mammoth niche appears to become drier, warmer, and more seasonal in terms of precipitation towards the end of the Pleistocene. To conclude, the environment occupied by proboscideans in North America did shift with time. More specifically, the niche space of mammoths changed more drastically than that of mastodons. Mammoth moved to occupy a niche space that was drier, warmer, and more seasonal in terms of precipitation, while mastodons more or less remained in a niche space that was wetter, colder, and more seasonal in terms of temperature. This data indicates that proboscideans, and mammoths specifically, were reacting to a change in the climate at the end of the Pleistocene. This data could also indicate competition between mammoths and mastodons, leading mammoths to shift into a different niche space to avoid further competition. Overall, we see significant shifts in the niche space of some proboscideans. However, there is still more data that can be collected and therefore room for these patterns to change. Thank you for listening to my presentation.